Hello, and welcome to the Smart Academy at the Smart family of cooling products. We're happy to have you here today for the Basic Refrigeration Cycle 101. In order to understand how refrigeration works, we have to really understand heat. When we do refrigeration, we are not adding cool to a space, but we are removing heat from that space and placing it somewhere more desirable. Heat is a form of energy. It can be described as molecules in motion. And the more molecular motion, the more speed that exists, the more heat that exists within that system. Now, how do we get rid of heat? Well, heat tends to want to get towards something with less heat energy. Energy states always want to equalize. So how do we accomplish that in a refrigeration system? Well, we would have to have something in the system that contained less heat energy than the air or the water that we're trying to remove that from. So take a look here, if you will, at my crude diagram here on the board. There are four basic components to any refrigeration system. And of course, there are many more parts that we can list in future videos. But these four main components exist in any refrigeration system. We have a compressor, a condenser coil, an expansion device, and an evaporator. Now, you can think about your compressor as the pressure increaser. The compressor actually increases the pressure on the high side and therefore creates a pressure decrease on the opposite side, on the suction side of the compressor. The condenser is where we first begin to drop high pressure to a lower pressure. In that condenser, we are in effect condensing below the condensing temperature. Then we have our expansion device. This can be thought of as the system pressure decreaser. So this is where your pressure is going to drop. Then we have your evaporator coil, which is where we will pick up all of that heat that is contained within the system. So let's take a look at an example here. If we have a refrigerant with a sitting temperature, and let's say our ambient temperature is 95 degrees. We would want to look then at a PT chart and find out what that refrigerant temperature should be at this ambient temperature, or what pressure it should be. So for R22, let's just say that we have a standing pressure on both sides of our compressor at about 150 psi. Now, when I give power to this compressor and I begin the refrigeration cycle, what's going to happen is this pressure is going to drop, while this pressure is going to raise dramatically. We may see a pressure on this side of about 78 psi, and this pressure here may go as high as 270. Now, how does that affect the rest of our refrigeration system? Well, take a look at this, if you will. A good example of this is what I'm about to show you here with a piece of ice. Here I've got this piece of ice in my hand. And if you hold it tightly, it may even create a little bit of pain in your hand. And over time, you notice that the ice begins to melt and to drip. Well, what's occurring here is that my body heat of 98.6 degrees is going into this ice of about 32 degrees. So my heat continues to enter into the ice, even changing the state of the ice to water. And if we wait long enough, that ice will cease to exist. So what has occurred is that ice has a lower energy state. There are less particles, molecules in motion within that ice. as opposed to my hand. Compared to the ice and the speed of the molecules in the ice, the molecules in my hand, the energy there is moving rapidly. And so that heat entered into the ice and melted it. So how can we create something within a refrigeration system that will have a lower energy state? Well, first, we have to kind of understand what a refrigerant is and what exactly it does. To understand a refrigerant, we have to know that refrigerants can exist at many different temperatures, just like everything else in nature. But at a given temperature, that refrigerant will also have a pressure to match. We call that saturated refrigerant temperature. So let's take one example of a common refrigerant that we use almost every day here at the Smart family. We will use R410A. At an ambient or outside temperature of 95 degrees, we use a PT chart to find 95 degrees Fahrenheit, which matches with 410A on the chart at 295. Now what is that 295? It's not a temperature, that's a pressure. Now what if I were to do the reverse? What if I said, well, what is 410A at 100 psi? I can look that up also right here on my PT chart. So find 410A and run down until we find 100 psi. psi is equal to 31.5 degrees Fahrenheit. Now, we call this saturated refrigerant temperature and pressure because at this pressure and this temperature, we have both liquid and vapor present. It's very important to remember that in your refrigeration system because we can alter that throughout the system. So let's take a look at a couple examples now. Let's begin our example starting at the compressor. Many refer to the compressor as the heart of the system, as without it we would have no pumping going on in the system. But the primary purpose of the compressor within a refrigeration system is to create a pressure differential in the system. Look at this example of 410A at 95 degrees. And again, we'll use our PT chart to find 95 degrees Fahrenheit. And that matches 295 psi. You would have 295 psi at every point within this system. Now, as soon as this compressor starts, on the high side, or discharge line, as we call it, the pressure would begin to increase. In a 410A system, you may see around 420 psi. But at the same time that we're increasing the pressure on this side, we're going to see a pressure decrease on the low side or suction side of the compressor. And this pressure will commonly be around 115 psi with a 95 degree ambient. Now, with this pressure increase across the system, we then send high temperature, high pressure refrigerant into the condenser coil. What comes out of the condenser coil is liquid because our refrigerant has dropped to a temperature at saturation. The liquid refrigerant then comes down towards our expansion valve. Now that all of that liquid has made its way from the condenser to the expansion device, the liquid is now forced through a small orifice, which then creates on the backside a flash gas, basically a mixture of liquid and vapor or saturated refrigerant. This saturated liquid vapor mixture is in the evaporator as air passes over. the air temperature at this point in your system is 95 degrees. At 95 degrees Fahrenheit, this air is crossing over this evaporator, which we have lowered the pressure and temperature of down to approximately 115 psi. At 115 psi on our PT chart, our refrigerant is 39 degrees. So we can say that our evaporator coil is 39 degrees Fahrenheit. Much like the ice example, the heat energy from the air is going to rapidly enter into the refrigerant. This will cause the refrigerant to boil because it is over its saturated temperature. As the heat is continually added, the refrigerant leaving the evaporator and traveling back to our compressor will be 100% vapor refrigerant because it has boiled off. Now, how can we tell if a refrigerant exists in the liquid or vapor state within our system? Because I can tell you that I have liquid leaving my condenser because I may have a sight glass. But how do I know that I'm 100% liquid? Or how do I know that I'm 100% vapor on the suction side? For this, you will need a set of gauges, and you will also need something to check the temperature of both your suction line and your discharge line, as well as your liquid line. Please follow along in this example with me. At 115 psi and 420 psi, our liquid pressure will probably be around 385 psi. I measure the line temp on each of these spaces, and I find that this line is about 58 degrees Fahrenheit. This is our suction line coming back to our compressor. Here on our discharge line, I also measure the temperature. I find that the temperature of this line is 171 degrees Fahrenheit. Now I go to my liquid line. I measure the temperature of the copper pipe, the actual line, and I find that this line is 97 degrees Fahrenheit. Now, I go to my PT chart and I look at 115 psi. At 115 psi, 410A refrigerant is 39 degrees. We can say that that is saturated refrigerant temperature. Now note, we actually measured 58 degrees. So we'll talk about that here in just a moment. Why is there a difference between what my pressure and my saturated temperature are versus what my actual line temperature is? Then we look at 420 psi. At 420 psi, 410A is about 121 degrees Fahrenheit. Notice again a drastic temperature difference between what I actually measure and what science tells us this refrigerant should be at this pressure. Let's look now at the liquid line. At 385 psi on our PT chart, we are around 115 degrees saturated refrigerant temperature. Now, why the difference in temperature versus what we measured on our line? The difference between the suction line temperature and the suction saturated temperature is called superheat. Superheat is heat that is added to a refrigerant after that refrigerant has changed state, has already boiled off. So after that liquid refrigerant has completely boiled away and just vapor exists, we were still absorbing heat. That heat is called superheat. And so the difference between 58 and 39 is 19 degrees. Therefore, we could say we have a 19-degree superheat. Here on our discharge line, we see a 50-degree temperature difference. This is called discharge superheat. Discharge superheat is where all the heat contained in the system can be found. Now we come to our liquid line. At 385 psi, remember that our saturated refrigerant should have been 115 degrees, but we measure on our line 97 degrees Fahrenheit. Well, the ambient air temperature at 95 degrees is still much cooler than the saturated refrigerant temperature within the coil. Therefore, we are still able to remove additional heat from that refrigerant after it became a liquid. The difference between 115 and 97 is 18 degrees. We call that temperature subcooling. Subcooling is heat removed after the state change to a liquid. So returning to our original question, how do we know what the proper charge is? How do we know how much refrigerant should be in the system and if we have enough refrigerant or if we have too much refrigerant within our system? The superheat and subcooling readings will tell us just that. A good superheat for any system is somewhere between 12 degrees and 17 degrees of superheat. On subcooling, we like to see about 15 degrees of subcooling. But let's examine what those numbers really tell us. When I tell you that I have 19 degrees of suction superheat, that means that I've picked up an additional 19 degrees of heat within my evaporator after the refrigerant boiled off. So if you would like a pictorial of that, look at the evaporator as if it were full of a liquid vapor mixture. If I have 0 degrees of superheat, I would have liquid all the way leaving my evaporator. That liquid refrigerant would then migrate its way to the compressor and possibly cause compressor damage. So superheat is important to us because knowing that that vapor exists and not liquid will keep our system running for many years. Now, what does it look like if I have superheat within my evaporator? Well, that means that my refrigerant boiled off somewhere around the middle of the evaporator. And now I've continued to add heat because my air temperature may be at this point around 80 degrees Fahrenheit. With a coil temperature of 39 degrees, there is going to be plenty of heat coming from the air into the refrigerant. That heat is called superheat. Heat gained after the state change. Now, what about subcooling? What does subcooling tell us? Well, subcooling tells us that not only have I condensed fully into a liquid refrigerant within my condenser, but I have condensed long enough for an additional 18 degrees of subcooling to take place, which means that my 95-degree ambient air is still cooler than my refrigerant temperature by 18 degrees.